So now let's talk about something called the Net Change Theorem. And what the Net Change Theorem is really another way of stating the fundamental theorem of calculus. This pretty much looks like the fundamental theorem of calculus part 2, except we're imagining that we're starting with capital F instead of starting with little f. So what this really says is if we start with some function capital F, and then we integrate its derivative, we get back to capital F. So again, it's explaining integration and differentiation as inverse processes. But really this has more of an applied sort of interpretation. If capital F represents some sort of quantity which changes over time or over distance or with respect to some other variable, then the net change theorem gives us a way of evaluating how much the quantity changes if we change the variable from A to B. Specifically, the change in the variable, or excuse me, the change in the quantity represented by capital F when changing x from A to B is the integral of the rate of change of f from A to B. So again, if I want to see, I take x is equal to A right now. What happens if I change x to B? How does f change? Well, to figure that out, we can integrate the derivative of f from A to B. The integral of the rate of change from A to B is equal to the net change from A to B. And we see net change here because, for example, if this is, say, position, and this is therefore velocity, this doesn't actually measure the distance you travel, it just measures the distance from where you started to where you ended, ignoring the specific path you took. So that's the net change aspect. All right, so here's an example. Let's consider a piece of wire, and we have it laid out along a horizontal axis. And let's imagine that the wire is not uniform in its mass. It changes as we move along. So, maybe this piece over here weighs more or less than this piece over here of the same length. Okay, so we can describe the scenario by letting m of x be the mass of this length of wire, the length of the wire from 0 to x. So if I just cut that piece off right there at x, how much does that weigh? When we take the derivative of m of x, we get something called the linear density. The thing is, let's think about what the units are here. M is a function of its mass. Its units are measured in mass. X is some length. It is a unit of distance, a unit of length. So the derivative is the change in mass with respect to the change in length. So its units are mass over length. Whenever you take mass over some geometric area, volume, whatever, you get a density. In this case, since we're taking the derivative with respect to, since we're dividing with respect to just length, it's linear density. All right, so that really just says how much does each incremental piece of the wire weigh, pretty much. Okay, so since the derivative of the linear density, of the mass is the linear density, then the net change theorem says that the integral from A to B of this linear density is the mass up to B minus the mass up to A. Well, if I take the mass up to B and subtract off the mass up to A, that's just the mass of the wire from A to B. Great. So if I integrate the linear density from A to B, I get the mass of the wire from A to B. Here's another example. Let's let P of t be the population at time t. Maybe t is years. If we're looking at world population or a country's population, or maybe t is hours if we're looking at the population of a culture of bacteria or something. Then P prime of t is the rate of growth. And I put absolute here in parentheses to mean that we're not talking about a percentage rate of growth. We're not talking about the population is increasing at a rate of 1% per year or something like that. We're talking about an absolute in terms of this is increasing by 1,000 individuals per year. 100 cells per hour, whatever. All right, then the integral of the rate of growth from A to B of P is equal to P of B minus P of A. That's the population at time B minus the population at time A. So that's the growth of the population between time A and time B. Now here's someplace where this idea of net growth is important, or a net rate of change, net change, because when you have a population, as it's growing, that implies that, you know, people are being born, or maybe people are moving in, or whatever. But at the same time, people can be moving out, people can be dying. The population, the rate of growth takes both of these into account. It's just talking about the actual population. It's not actually just counting births and ignoring deaths or whatever. So this net change here includes how many new people are there minus how many people have left. Let's do an economic sort of example. So let's let C of X be the cost of producing X goods. And so X could be, you know, computers, the number of computers that a company makes, or maybe the company makes chemicals. So X is the number of liters it produces, whatever. And MCX is the marginal cost of the Xth good. It's the derivative of C with respect to X. And the interpretation here is, okay, we're making, say, 10 goods. How much is the 11th one going to cost to make? And that's the marginal cost of the 11th good there. So that'd be MC of 11. Now, this matters in economics because, for example, in the model of perfect competition, we will choose our production level X so that the marginal cost is equal to the price, because you generally assume that the marginal cost is going to be increasing beyond some point. So you really choose the largest X so that the marginal cost is equal to the price. Why would you make, you know, if the marginal cost is increasing beyond X, why would you make another good if it costs you more than you're going to earn back? Anyways, so the net change theorem here says that the integral from A to B of the marginal cost of X dx is C of B minus C of A. It's the additional cost of increasing production from X equal to A to X equal to B. So if I just add up here, thinking of the integral as a sum, if I add up the marginal costs of the 8th good through the bth good, that should give me the additional cost of increasing production from A to B. All right, I'd like to emphasize once again that this is really the net change theorem, which is really just saying what's the difference between where I am at B versus where I was at A. And one of the best ways to illustrate this is via position and velocity. So if S of t is a position function telling us where we are along an axis at time t, and v of t is the velocity, so that if it's positive it means we're going this way, negative means we're going that way, then the integral from a to b of v of t is s of b minus s of a. It's just the distance between where I am at time b and time a. It doesn't matter if I went back and forth between them 100 times over this time interval from a to b, so long as I'm just integrating the velocity. All that matters is the net change, just the distance from where I started and where I ended. Furthermore, you could end up with a negative number here, and that would mean that I started over here and I ended up over here. So I traveled in the backwards direction overall. If you wanted to get, say, the distance that you traveled from time equal a to time equal b, you would need to take the integral from a to b of the absolute value of the velocity. That will give you the distance traveled. So here's question 2. If v of t, the velocity of some object moving along an axis, is negative 6 plus 3t for time between 0 and 5, evaluate first a, the definite integral from 0 to 5 of v of t dt, and b, the distance that this object has traveled from time equals to 0 to time equal to 5. I gave you the formula for doing that in the previous example, or the previous shot, which was just put the absolute value bars around v of t. But to actually evaluate this, here's a hint. break the integral into two integrals, into one over an interval where the velocity is negative, the other where the velocity is positive.